Hi, welcome back to the class. In this class, we'll be learning about functions. Knowingly or unknowingly, we rely on so many persons for so many things. Man is an intelligent species, but still cannot perform all of its life tasks all alone. He has to rely on others. You may call a mechanic to fix up your bike, or rely on a store to supply you groceries every month. A program finds itself in a similar situation. It cannot handle all the tasks by itself. Instead, it requests other programs like entities called functions in C to get its tasks done. In this class, we will study these functions. We will look at variety of features of these functions, starting with the simplest one and then working towards those that demonstrate the power of functions. What is a function? A function is a self-contained block of statements that performs a coherent task of some kind. Every C program can be thought of a collection of these functions. As we have noted earlier, using a function is something like hiring a person to do a specific job for you. Sometimes the interaction with this person is very simple, sometimes it's complex. Suppose you have a task that is always performed exactly in the same way, say a bi-monthly services of your motorbike. When you want it to be done, you go to the service station and say, "It's time, do it now." You don't need to give instructions because the mechanic knows his job. You don't need to be told when the job is done. You assume the bike would be serviced in the usual way. The mechanic does it and that's that. Let us now look at a simple C function that operates in the same way as the mechanic. Actually, we'll be looking at two things, a function that calls or activates the function and the function itself. And here, the output is smile and the world smiles with you, cry and you stop the monotony. Here, the main itself is a function, and through it, we are calling the function message. What do we mean when we say that main calls the function message? We mean that the control passes to the function message. The activity of main is temporarily suspended. It falls asleep while the message function wakes up and goes to work. When the message function runs out of statements to execute, the control returns to main, which comes to life again and begins executing its code at the exact point where it left off. Thus, main becomes the calling function, whereas message becomes the called function. If you have grasped the concept of calling a function, you are prepared for a call to more than one function. Consider the following program. For this program, a number of points has to be noted. Any C program contains at least one function. If a program contains only one function, it must be main. If a C program contains more than one function, then one and only one of these functions must be main because program execution always begins with main. There is no limit on the number of functions that might be present in a C program. Each function in a C program is called in the sequence specified by the function calls in main. After each function has done its thing, control returns to main. When main runs out of function calls, the program ends. As we have noted earlier, the program execution always begins with main. Except for this fact, all C functions enjoy a state of perfect equality. No precedence, no priorities, nobody is nobody's boss. One function can call another function it has already called, but has in the meantime left temporarily in order to call a third function, which will sometime later call the function that has called it. If you understand what I mean. No? Well, let's illustrate this with an example. Here, main calls the other function, which in turn calls still other functions. Trace carefully the way control passes from one function to another. Since the compiler always begins the program execution with main, every function in a program must be called directly or indirectly by main. In other words, the main function drives the other functions. Let us now summarize what we have learned so far. A C program is a collection of one or more functions. A function gets called when the function name is followed by a semicolon. For example, a function is defined when function name is followed by a pair of braces in which one or more statements may be present. For example, Argentina with multiple statements in it. Next, any function can be called from any other function. Even main can be called from another function. For example, main here is being called by another function. A function can be called any number of times. For example, the function is being called more than once in this particular example. The order in which the functions are defined in a program and the order in which they get called need not necessarily be the same. Like you see in this example, the order specified is not same as the order executed. Here, even though message 1 is getting called before message 2, still message 1 has been defined after message 2. However, it is advisable to define the functions in the same order in which they are called. This makes the program easier to understand. A function can call itself. Such a process is called recursion. We would discuss this aspect of C functions later in the class. A function can be called from another function, but a function cannot be defined in another function. Thus, the following program code would be wrong since Argentina is being defined inside another function, main. There are basically two types of functions: library functions, example printf, scanf, etc., and user-defined functions, example Argentina, Brazil, etc. As the name suggests, library functions are nothing but commonly required functions grouped together and stored in what is called a library. This library of functions is present on the disk and is written for us by people who write compilers for us. Almost always, a compiler comes with a library of standard functions. The procedure of calling both types of functions is exactly the same. Why use functions? Why write separate functions at all? Why not squeeze the entire logic into one function, main? The basic reasons are: writing functions avoids rewriting the same code over and over. Suppose you have a section of code in your program that calculates area of a triangle. If later in the program you want to calculate the area of a different triangle, you won't like it if you are required to write the same instructions all over again. Instead, you would prefer to jump to a code of section that calculates area and then jump back to a place from where you left off. This section of code is nothing but a function. Using a function, it becomes easier to write programs and keep track of what they are doing. If the operation of a program can be divided into separate activities and each activity placed in different functions, then each could be written and checked more or less independently. Separating the code into modular functions also makes the program easier to design and understand. So what is the moral of the story? What I would suggest you to do is to not cram the entire logic into one function. It is very bad style of programming. Instead, break a program into small units and write functions for each of these isolated subdivisions. Don't hesitate to write functions that are called only once. What is important is that these functions perform logically isolated tasks. Passing values between functions. The functions that we have used so far haven't been very flexible. We call them and they do what they are designed to do. Like our mechanic, who always services the motorbike in exactly the same way, we haven't been able to influence the functions in the way they carry out their tasks. It would be nice to have a little more control over what functions do. In the same way, it would be nice to be able to tell the mechanic, also change the engine oil, I am going out for outing. In short, now we want to communicate between the calling and the called functions. The mechanism used to convey information to the functions is the argument. You have unknowingly used the argument in the printf and scanf functions. The format string and the list of variables used inside the parentheses in these functions are arguments. The arguments are sometimes also called as parameters. Consider the following program. In this program, in main, we receive the values of a, b, and c through the keyboard and then output the sum of a, b, and c. However, the calculations of sum is done in a different function called calsum. If sum is to be calculated in calsum and values of a, b, and c are received in the main, then we must pass these values to calsum, and once calsum calculates the sum, we must return it from calsum back to main. There are a number of things to note in this program. In this program, from the function main, the values of a, b, and c are passed on to the function calsum by making a call to the function calsum and mentioning a, b, and c in the parentheses. Sum is equal to calsum in brackets a, b, and c. In the calsum function, these values get collected in the three variables x, y, and z. The variables a, b, and c are called actual arguments, whereas the variables x, y, z are called formal arguments. Any number of arguments can be passed to a function being called. However, the type, order, and number of actual and formal arguments must always be the same. Instead of using different variable names x, y, and z, we could have used the same variable names a, b, and c, but the compiler would still treat them as different variables since they are in different functions. There are two methods of declaring the formal arguments. The one that we have used in our program is known as Kernighan and Ritchie, or just K and R method. Calsum in parenthesis x, y, z, int x, y, z. Another method is to mention calsum, int x, int y, and int z. This method is called as ANSI method, ANSI, and is more commonly used these days. In the earlier programs, the moment closing brace of the called function was encountered, the control returned to the calling function. No separate return statement was necessary to send it back. This approach is fine if the called function is not going to return any meaningful value to the calling function. In the above program, however, we want to return the sum of x, y, and z. Therefore, it is necessary to use the return statement. The return statement serves two purposes. On executing the return statement, it immediately transfers the control back to the calling program. It returns the value present in the parenthesis after return to the calling program. In the above program, the value of sum of three numbers is being returned. There is no restriction to the number of return statements that may be present in a function. Also, the return statement need not always be present at the end of the called function. The following program illustrates these facts. In this function, different return statements will be executed depending on whether ch is capital or not. Whenever the control returns from a function, some value is definitely returned. If a meaningful value is returned, then it should be accepted by the calling program by equating the called function to some variable. For example, sum is equal to calsum in parenthesis a, b, c. All of the following are the valid return statements. Return in parenthesis a, return 23, return 12.34, and a return with no parentheses at all. In this case, a garbage value is returned to the calling function since we are not returning any specific value. Note that in this case, the parentheses after return are dropped. If we want that a called function should not return any value, in that we must mention so by using the keyword void as such below. A function can return only one value at a time. Thus, the following statements are invalid. There's a way to get around this limitation, which would be discussed later on when we're learning about the pointers. If the value of a formal argument is changed in the called function, the corresponding change does not take place in the calling function. For example, the output of the above program would be 60 and 30. Thus, even though the value of b is changed in fun, the value of a in main remains unchanged. This means that when the values are passed to a called function, the value present in actual arguments are not physically moved to the formal arguments. Thus, just a photocopy of values in actual argument is made into formal arguments. Scope rule of functions. Look at the following program. In this program, is it necessary at all to pass the value of the variable I to the function display? Will it not become automatically available to the function display? No, because by default, the scope of a variable is local to the function in which it is defined. The presence of I is known only to the function main and not to any other function. Similarly, the variable k is local to the function display and hence it is not available to main. That is why to make the value of I available to display, we have to explicitly pass it to display. Likewise, if we want k to be available to main, we will have to return it to main using the return statement. In general, we can say that the scope of a variable is local to the function in which it is defined. Calling convention. Calling convention indicates the order in which arguments are passed to a function when a function call is encountered. There are two possibilities over here. Arguments might be passed from left to right, or arguments might be passed from right to left. C language follows the second order. Consider the following function call. In this call, it doesn't matter whether the arguments are passed from the left to right or right to left. However, in some function call, the order of passing arguments become an important consideration. For example, it appears that this printf will output 1, 2, 3. This, however, is not the case. Surprisingly, the output is 3, 3, 1. This is because C's calling convention is from right to left. That is, firstly, 1 is passed through the expression a plus plus and then a is incremented to 2. Then result of plus plus a is passed. That is, a is incremented to 3 and then passed. Finally, latest values of a, that is 3, is passed. Thus, in right to left order, 1, 3, 3 gets passed. Once printf collects them, it prints them in the order in which we have asked it to get them printed, and not the order in which they are passed. Thus, 331 gets printed. 1DC issue. Consider the following function calls. Here, we are calling 3 standard library functions. Whenever we call the library functions, we must write their prototype before making the call. This helps the compiler in checking whether the values being passed and returned are as per the prototype declarations. But since we don't need define the library functions, we merely call them. We may not know the prototypes of library function. Hence, when the library of functions is provided, a set of .h files is also provided. These files contain the prototypes of library functions. But why multiple files? Because the library functions are divided into different groups and one file is provided for each group. For example, prototypes of all input and output functions are provided in the file stdio.h. Prototypes of all mathematical functions are provided in the file math.h, etc. On compilation of the above code, the compiler reports all errors due to the mismatch between parameters in function call and the corresponding prototypes declared in the function conio.h. You can even open this file and look at the prototypes. They will appear as shown below. Now consider the following function call. These functions get successfully compiled even though there is a mismatch in the format specifiers and the variables in the list. This is because printf accepts variable number of arguments, sometimes 2 arguments, sometimes 3 arguments, etc. And even with the mismatch above, the call still matches with the prototype of printf present in stdio.h. At runtime, when the first printf is executed, since there is no variable matching with the last specifier %d, a garbage integer gets printed. Similarly, in the second printf, since the format specifier for j has not been mentioned, its value does not get printed. Next, going to advanced features of functions. With the sound basis of the preliminaries of C functions, let us now get into their intricacies. Following advanced topics would be considered here: function declaration and prototypes, calling functions by value or by reference, and recursion. Let us understand these features one by one. Function declaration and prototypes. Any C function by default returns an int value. More specifically, whenever a call is made to a function, the compiler assumes that this function would return a value of the type int. If we desire that a function should return a value other than an int, then it is necessary to explicitly mention so in the calling function as well as in the called function. Suppose we want to find out square of a number using a function. This is how the simple program would look like. And here are the 3 sample runs you would like to use. The first of these answers is correct, but square of 1.5 is definitely not 2. Neither is 6, a square of 2.5. This happened because any C function by default always returns an integer value. Therefore, even though the function squares calculates the square of 1.5 as 2.25, the problem crops up when this 2.25 is to be returned to main. Square is not capable of returning a float value. How do we overcome this? The following program segment illustrates how to make the square capable to return a float value. And here is the output. Now, the expected answer, that is 2.25 and 6.25, are obtained. Note that the function square must be declared in main as float square in parenthesis float. This statement is often called the prototype declaration of the square function. What it means is, square is a function that receives a float and returns a float. We have done the prototype declaration in main because we have called it from main. This is a possibility that we may call square from several other functions other than main. Does this mean that we would need prototype declaration of square in all these functions? No. In such a case, we would make only one declaration outside all the functions at the beginning of the program itself. In practice, you may seldom be required to return a value other than an int, but just in case you're required to, employ the above method. In some programming situations, we want that a called function should not return any value itself. This is made possible by using the keyword void. This is illustrated in the following program. Here, the gospel function has been defined to return void, which means it would return nothing. Therefore, it would just flash the 4 messages about viruses and return the control back to the main function. Coming to call by value and call by reference. By now, we are well familiar with how to call functions. But if you observe carefully, whenever we call a function and pass something to it, we have always passed the values of variables to the called function. Such function calls are called call by value. By this, what we mean is, on calling a function, we are passing values of variables to it. The example of call by value are shown. We have also learned that variables are stored somewhere in the memory. So instead of passing the value of a variable, can we not pass the location number of the variable to a function? If we were able to do so, it would become call by reference. What purpose a call by reference serves, we would find that out a little later. First, we must equip ourselves with the knowledge of how to make a call by reference. This feature of C function needs at least an elementary knowledge of a concept called pointers. So we will be learning in the next class the concept of pointers. Thank you.